Hello, today we want to have a final discussion in this huge renormalization program we have been following, right? And the idea today is to compare the results we obtained in the last video with a system in condensed matter, right? The advantage here is that we have more intuitive understanding of especially non-relativistic systems, and we'll be able to see a very specific and clear example on how a running mass works, right? Because in this case, the interpretation of these Wilson coefficient for the quadratic term on the field really shows up as just a running term in a potential that is changing as you run along, right? So we want to take a look at that. The system we choose to look at first is some system that can go undergo magnetization, right? And we'll use the Landau theory to look at phase transitions for that material. And my main assumption here will be that the material has one preferred axis of magnetization. So despite being a 3D material, right, the magnetization, the total magnetization, can be measured just as a number, right, which can be positive if it is along this axis, or negative if it goes against, and or zero, right? And for small regions of the material, then I can define some spin alignment density, right? I can say that the magnetization is the integral all over the material of this S of X, which measures local magnetization also along that axis. So S is just a number, right? And essentially a scalar field living in 3 dimensions, right? X here can be a positioning in 3 dimensions, right? You have to notice that by doing that assumption, I'm fixing the degrees of freedom for my field theory to be just this scalar field, right? And I want to know details about the total magnetization of the material using this guy, right? So now I want to justify the Gibbs free energy for this system, right? I can start by noticing that if the temperature is low enough, right? Suppose we're a very low temperature first. So the first situation we want to think about is this. T is close to 0, right? And also I'll define, so already I define the magnetization here, right? I define this spin density or magnetization density, right? And I want to also define an external field, right? Because I can also force magnetization by putting this material under a strong external magnetic field, right? And to start with, let's think this is not present. So I'm thinking of the situation where I have small temperature and 0 external field, right? Under that situation, right, I can have some total magnetization, right? Because at 0 temperature, the material, the alignment of the spins can happen spontaneously, right? And the material will choose a direction, either positive or negative M, right? Can be parallel or anti-parallel to this axis, but that is random, right? You don't know in which direction it will be, right? So we'll have an M which is different from 0, right? But we don't know the direction of this M. It can be either direction. Now suppose I keep the temperature low, but I now change the magnetic field. So now the external field can be different from 0, right? Now even a very small external field can determine the direction of the total magnetization of the material, because it's not random anymore. Even a very small external magnetic field near 0 temperature will force a number of spins to align with the external field, and then the whole material will align, right? So now you have, or at least a big part of the material can align, right? So H bigger than 0 favors M bigger than 0, and H smaller than 0. That again, I'm measuring this external field as a projection in this direction. You can even assume that I'm only turning on this magnetic field in the same direction of these preferential axis to simplify stuff, right? So it's also the external magnetic field will be just a number, which can be positive or negative, right? And it favors these two situations, right? That tells us something important, right? Because I can go continuously from negative external field towards positive external field, growing through zero external field, right? But the magnetization will not change continuously from negative to positive, because even at zero external magnetic field, I still have some magnetization. And that tells us that here we have this continuous change in the order parameter, right, which is the magnetization, and that is a first order phase transition right there, right? If I change the external magnetic field slowly from negative to positive, I'll have a discontinuity in the magnetization. It will still be different from zero as I get to zero external magnetic field, and once I change to the other side, it has to change quickly to a different magnetization, right? And so that's the first observation. Now we want to know what happens as I increase temperature, right? So we're thinking of a situation where T is bigger than 0, right? And the external field is 0. At first, as I increase the temperature, keeping the field 0, not much happens. All you notice is that temperature is working against this spontaneous alignment of the spins that is happening here. And as the temperature goes up, let's indicate it like that, right? The total magnetization, I'll put in module here because it could be positive or negative, but it goes down, right? Still different from 0, but as I increase the thermal effects, right, the disorder, right, the spontaneous magnetization diminishes, right? That goes on up to some critical temperature, right, which is exactly defined by this condition, right? As I increase my temperature, the magnetization goes down, right, but it's still not 0. At that critical temperature, so that's this another situation, right? At some point, I will go over that critical temperature. So now T is bigger or equal to this critical one, right? The external field is still 0, right? At that point, finally, the thermal effects are winning over the natural alignment of the spins, right? And the magnetization has become 0, right? And that's a critical point in my theory, right? Or a second order phase transition, right? Now I'm going from a situation where I can go continuously from negative M to positive M as I change the external field, right? Now I need a fairly big external field to align spins and magnetize my material. As I lower my magnetization, my external field, the magnetization goes to 0, and then I have to force it the other way to increase it away from 0, right? So let me show you a diagram of these this situation. So here you see both the low temperature regime and the high temperature regime. This axis is the temperature, right? And this axis is the external field, right? And all these situations are described in this plot, right? So you can see that if you keep the temperature really low and you change your magnetization from negative to positive, you go through a discontinuity in this magnetization because it is positive on one side and negative in the other, right? Of course, if you sit along this line, both situations will coexist in different regions of the material, right? And that is true up to this critical temperature, because above it, now the temperature, the magnetization is zero, and you can go from one side to the other continuously. In fact, you only have a strong magnetization if you now force it with a fairly strong magnetic field, because near zero the temperature, the magnetization is zero, right? So now we're interested in this point, right? Of course, this is the most interesting point in this whole diagram, and we want to focus what happens as we go through this point in some direction. The first thing to notice is that our magnetization is the order parameter for this phase transition over the critical temperature, right? And that I can write the free Gibbs energy for this theory as the derivative of the magnetization at constant temperature, right? And that needs to be equal to the external field. That's the definition of my free Gibbs energy for this system, right? Also, near the critical point, right, whatever happens, the magnetization is fairly small, right? Either on this side or this side, I'm already going towards the point where the spontaneous magnetization is zero, right? And also I'm close to where the external field is close to zero. So the magnetization is small either way. And that means that this is a function of magnetization, which can now be written as a polynomial in the magnetization, right? I'm just Taylor expanding and stopping at some point, which I choose to be a power 4, right? You see, so I have some constant independent of the magnetization, some term that depends on the magnetization square, and some other term dependent on the magnetization to the power 4. And you might notice that I'm skipping the odd powers of the magnetization, right? And that's because I'm assuming that the material is symmetric, right? It has a preferred axis of magnetization, but not a preferred direction, right? So I'm not favoring positive or negative magnetization, and now that's where the symmetry is coming, right? I'm assuming some symmetry. So that's I want you to notice that this is very similar to how we have been building these relativistic quantum field theories. So I decided first on the degree of freedom. It's just one number, right? S, right? Here I decided my magnetization density can be described with just one number, right? And now I'm deciding that's also symmetric, right? I'm not favoring positive or negative, so I can only have even powers of the magnetization here, right? So that's my model. Of course, the behavior of my system depends on temperature, and that means that these coefficients of the polynomial in M are temperature dependent, right? That's very important. Now, if I want to know the behavior of this system, right, I have to solve this equation. The first situation I want to think about is the one in the absence of an external field, right? And then this equation becomes just the minimization of this potential, right? I'll have to solve for this equal to 0. And so I just have to analyze where is the minimum of this potential up here. Right? That's easy to see. There's essentially two cases I want to look at. Right? The first one, this does not matter at all, right, for the minimum. but these two guys do, right? If both B and C are bigger than 0 at some temperature, right? That will depend on temperature. But suppose we're first looking at a situation where both are positive, right? Then my potential looks like this, right? So let me draw it. I just need these two axes, one for the magnetization and one for the energy, the free energy, right? And if both B and C are positive, both the square part and the power 4 part of the potential are positive, you have something like that, right? And then, of course, the minimum sets the total magnetization equal to 0. So you have at first this situation. If both of these guys are positive, you expect the magnetization to be 0. Now, suppose a different situation where C is still positive, right? And that is a constraint I don't want to ever give up on, because otherwise this potential will be unbounded from below, and then I cannot minimize the energy, right? But suppose that above or at some temperature, right, this guy is negative. At some temperature, this guy is negative. Now I have a different situation, right? Because now the square part of my potential, let me stretch these axes down, right? Now the quadratic part at first is like that, right? But eventually the power 4 wins, the quartic part wins. This should be symmetrical. I cannot draw properly, but imagine it's completely symmetrical, right? Now I have two different minima, right, with opposite magnetization. So here I have a negative magnetization, and here I have a positive one, right? Exactly the same number, right? So I have a symmetric thing, but opposite magnetizations are favored at this second situation, right? You see where I am going with this. These models quite perfectly what I have here, right? At first I have a minimum for 0 magnetization, and then I have two minima, right, at opposite magnetizations, and there's nothing favoring one over the other, right? That's exactly these two situations. So I want this to be true on this side, right? And this second situation to be true on this side of the critical temperature, right? The easy way of modeling this, right, is to assume, again, for simplicity, and all I need is for these assumptions to be true near the critical point. I'm not going too far away from it, right? So assume that, let me write it like that, that C of t, right, is just constant. So I have a constant. I'll use a lowercase c for this constant, independent of temperature, so the quartic part is not changing at all, and have the square part to depend on the critical temperature, so that it is positive above the critical temperature and negative below the critical temperature. And there's an easy way of doing that, right? Again, I define a lowercase b because there's always some constant here, but I assume the following temperature dependence, right? Which defines the critical temperature again, right? According to what I wanted it to be, right? So at this critical temperature, it becomes, right, below, for t smaller than Tc, B is negative, and for t bigger than Tc, this is B of t is positive, right? Again, just to make everything clear, B and C are positive, right? So so that the sign is only coming from here, and in this case I'm just guaranteeing there is a minimum, right? So in this case, what we have for the magnetization now is what we wanted. So again, I'm talking only at 0 external field so far. My magnetization will be 0 for t bigger than Tc, and plus or minus, right? And now I just have to solve this equation, right? So I can take this potential, actually write my del G del M at constant t equal to 0, right? And actually differentiate on this guy. That will give me 2b of t m plus 4c of t m cube equal to 0, right? Actually, the equal to 0 is already on that side. I just have to solve this equation. There's a solution for m equals 0, which is that one, right? And a second one for actually that at lower temperature, there's one solution, which is this unstable one here, right? And the other two solutions are just m squared. I just have to solve this, right? And what I get is this plus or minus b over 2c tc minus t to the power half, right? So this the thing inside the square root here is positive, and I have two solutions for t smaller than tc, right? This is a solution of this equation. You just have to substitute b and c here and solve for the solution other than m equals 0, which is this point, which does not interest us, right? So there you go. Those are the two solutions for external field equals 0. Now, if we take h different from 0 now, right, we have to solve again for this equation, right, which is equivalent. Let me copy it here, right? And that's the same as minimizing in relation to m a different potential, which I can call GMH, right? Which is AT, nothing changed here, right? So this is BT M squared plus CT M fourth minus HM, right? If I differentiate this in relation to M and set it to 0, I get this equation, right? And you can see immediately how adding this term to the potential does exactly what we wanted, right? Because now if I add a linear term to this previously quadratic plus quartic potential, what I'll do is I'll change the minima so that, for instance, when h is positive, right, I'll favor the potential will be something like that, right? Because if h is positive, I have a negative linear contribution, and I favor positive magnetization. And if h is negative, then this one will be lower, this one will be higher, and I favor negative magnetization. So you see, this is doing exactly what we wanted, right? And now this basically sets the potential for the field theory I want to build. I can take this first term equal to 0 without any laws of generality, right? It's just the overall height of this free energy, right? And now what I want to do in order to write this as a field theory is to remember that the magnetization can be written as this integral over the volume of the material of the magnetization density. So I can write G as an integral over d3x, right? Of something, I'll leave some space here for an extra term I want to add. Now I have B of t, which I have parameterized as lowercase b t minus tc times s squared, right? Here, same is lowercase c, so b and c here are just numbers that if I want to know, I really have to measure, right? And I have here s to the fourth, right? And these I will exchange by hs, right? And in every case, I'm assuming that I can do that locally, right? So I'm replacing m4 by s to the fourth because I'm making a local energy, right? Now there's an extra term I have to add so that this S field has some dynamics, right? Luckily, that's also implementing an important dynamic for the system, which is the tendency of spins to align, right? This is equivalent to a kinetic term, not a potential one, right? But you can see that if I put a kinetic term like that, that's the simplest way considering the symmetries of the problem, right? I cannot have a linear term in S to force the spins to align because I'll be minimizing this, right? And as I minimize gradients, I enforce this tendency of the spins to align. So now I have a three-dimensional field theory for this field here, right? And I can use either field theory methods or just minimizations, right, to solve for configurations of this system, right? Notice also that now, since I put the integral out here, right, I'm changing my external field, which I have been treating as a constant field over all space, right, to a function of x, right? So now I can have a more complicated configurations for this external field. In fact, the one I'm interested at now is one that I really have set this field at a particular point. So suppose now I adopt a configuration for this external field, which is very localized at the origin. So this is just a number, h naught, but the configuration in space is really a Dirac delta at the origin, right? Why I'm doing that? What I want to see is what happens when I put a really strong but really localized field, right, at the origin. What happens at the origin is quite easy, right? If this is big enough and I Dirac delta is really big, right, I know that the magnetization at that point is aligned with H naught, right? If this is positive, I'll have a positive S there, and if this is negative, S will be negative at that point, right? But now I want to look around that point, away from the origin, right? And see how correlations propagate. How far, if that is spin, I'm forcing the spin at that point to be pointing up, let's assume H naught is positive, right? How far away from that point I have to go before other spins, because the spins around it will tend to align in the same direction I'm forcing this one. How far away do I have to go to not notice that effect anymore, right? So let's see. In order to answer that question, I have to see how the configurations of S are if X is different from 0. So I want to look at X different from 0, and I want to know what is the form of this function, right? Away from that origin, right? First, let's think of the situation where T is bigger than the critical temperature at first, right? So the configuration of S is obtained by this equation, right? Delta G of S is set to 0. If I use this expression for G, right, my variation of G, I just have to make the variation in relation to S, right? This first term will be just this. The second one is 2B times T minus TC times S, right? This one is 4C times S cubed. And the last one is just minus H, right? And this is the equation I need to solve. Now I want to solve this equation for this situation, right? Which allows me a few considerations, right? First is that at X different than 0, this guy is 0, right? For X different than 0, let me put it like that. X not 0, this guy is 0. And the second one is for temperatures above the critical temperature, right? I can assume the magnetization is small, right? And that, especially if I have no external field, right? And I will use that to disregard the S cubed term. Let me put a decent 3 here. So this will be essentially 0. So I get rid of these two last terms, right? And notice that in terms of a field theory, what I'm doing here is looking at the free theory, right? I'm ignoring the source and I'm ignoring the interaction, right? And this is why I can do that in this case, right? In that case, I get a pretty simple expression. So remember, I'm talking about this situation now. And for this situation, I can ignore those two terms and get an equation, which is essentially just this part, if I manage to copy it, right? And I can put an S in front here, right? And write it like this, right? This is 0 away from that point and different from 0 at X, right? This is nothing but a green function, right? If I substitute this for a Dirac delta, I can call this guy just to make a difference between a general solution for S from this particular one, right? Where I'm using H equal to H naught times delta 3 of X, right? And we know the solution to this, right? This is a green function. This is nothing but the propagator in 3 dimensions, right? We can guess the solution. In this case, is just dx is equal to d3k 2 pi cubed h naught, because here we have a this normalization, right? Exponential I kx over k square plus this thing here to be t minus tc, right? And this is now start noticing that this guy is playing this role that you would have with a mass here, right? A mass square for some excitation of this field if we were talking about a field theory of particles, right? I can do this integral, right? It's not hard. We did one very similar to it when we were figuring out the Yukawa potential, right? The solution is actually simple one, is just this, where r here is the distance to the origin, right? And you have some exponential of minus r psi, where psi is defined from this piece right here, right? I'm calling this 1 over psi square, right? It's kind of 1 over the mass, if this was a mass, right? And you see, this is the thing that sets the correlation distance, right? This thing is suppressing exponentially, right? Spins to be aligned to the one I set at the origin, right? At distances of order psi, right? This is when r becomes comparable with psi, I have or bigger even, I have an exponential suppression, and that's a good definition of our correlation distance. Remember, my question is how far away I had to go from the origin before I stopped noticing this H naught alignment, right? That if H naught is positive, then the spins will also be positive away from the origin at a distance psi. So writing it explicitly, my psi was defined. Let me put it here as to be t minus tc to the power minus half. And that's the important result we wanted from this Landau theory for the phase transition for this system. Now there are a few things we need to notice because this is getting really rich in terms of interpretation, right? The first thing to notice is that B and C that appear here in my free energy, they are really dependent on the ultraviolet completion of this theory, right? What happens at microscopic scales, right? I'm already treating this material using a field theory, so I'm talking about regions, right? Where I can define this spin density. So I integrated out the details of the individual spins. And that is included, of course, in the Wilson coefficient of these operators. So that's where the details, the microscopic details are encoded in B and C. On the flip side, let's look at this correlation distance, right? This thing, of course, depends on B, but the way it scales with temperature, right, is not dependent on B. What I'm seeing here is that psi grows as I get near the critical temperature, and it grows in this way, right, with this power of minus 1/2 of this distance to the critical temperature, right? I'm coming from above the critical temperature and approaching it, and the correlation distance grows, right? This minus half is not dependent on B, right? And it depends only on the symmetry, right? This is coming from the fact that the free energy had this particular shape, right, in terms of these powers of this field S that were present or not, right? So the symmetry is setting the scaling. And the fact that this scaling can be independent on the details, the microscopic details of the material, is what is called universality, right? And this is very closely related to the fact that quantum field theories can be cut off independent, right? We'll see in a second, but the fact is that at long distances, as I go away from the material, I'm not sensitive anymore to these details, right? This scaling is independent of them, right? The second thing I want to notice is, it's already being shown here, right? Is that we are developing long distance correlations near this critical temperature. You can see from this scaling that if T goes really close to Tc, then the correlation length is diverging, right? You're essentially killing this exponential suppression, and then you just have a 1 over r distance, which is a long distance correlation, right? That's what we call a long distance correlation. On the flip side, what happens if I'm far away from the point where this is 0? Then the thing that will dominate here, the typical correlation distance, is B, right? And B is, again, dependent on the ultraviolet of the theory. And if you look here, it has dimensions of mass square, right? Of momentum square in this case. So if since this guy is set by the UV of the theory, if this is doing nothing special, is not specially small, B will be of order, right, lambda square, right, which is equivalent, if I call this a mass, right, if I say this is some sort of mass for this theory, right, that means that mass is of order lambda, right, and the correlation length will be of the order, or lambda here is my cutoff for this theory. We know that this theory has a physical cutoff, right, which is given by the distance between these atoms in my material, right? So what I'm saying is that if I go too far away from the critical temperature, my typical correlation distance will be just at the same size of the distance between atoms, which means I'm just saying that just neighbors, right? There will be just nearest neighbor correlations and nothing beyond that. So if you look at the material at long distance, there's no correlation. The material will be completely disordered, right? Which is what you expect for higher temperatures than the critical temperature. See, so again, we're getting what we expect, right? And you see that has a nice interpretation that for T very different from Tc, I can describe this as a field theory with a heavy particle, right? And heavy particles don't propagate too far, right? You see again that I'm seeing that this correlation maps really nicely to a propagator for a particle with this mass, right? And if this mass is too big, the particle doesn't go far, right? But if I'm near the critical temperature, then the mass of this particle can be much smaller than lambda, because this number now, this T minus Tc here, is getting small, so as to compensate for the fact that B is big, right? And I can get a small mass, so long, and then I have a particle which is communicating points in this material, a quasi-particle in this case, right? If I use the proper term, right? Which is communicating points in the material which are distant from each other. If the mass is small, it will go over long distances, and creating long distance correlations. So you see, you can talk about this both in terms of these correlations or through the propagation of some quasi-particle that communicates different parts of the material, right? And the third point I want to call attention to is that this particle that is doing this communication is essentially a virtual particle, right? And the mass that we're talking here, right, is not really the pole mass of any asymptotic state, right? Really what I'm talking here is about how this term changes the potential and the long distance correlations. And it makes total sense that this term should be running parameter of my theory. Of course, it depends on the scale. In this case, it's temperature they're showing up here, right? But you can think of temperature at the typical scale of momenta, right? And so it makes total sense that the shape of this potential, potential changes, right, as I change my temperature. And that's why we have this mass, which is a running mass, right? With that in mind, we can apply all the formalism that we did in the last video. Now we can replace this theory by a matching, right? I just have to match this mass in this way, right? And I can do lambda phi 4, right, as the dimensions go to 3, right? We did lambda phi 4 in 4 dimensions a lot, right? But in the last video, we did show some results for d smaller than 4, and now we can propagate those results all the way to dimensions equal 3 and use the results we had before to study the running of these mass, so to speak, right? You can think of it as a mass, a running mass, or a changing correlation length, right? It's the same. So let's spend a few minutes looking at lambda phi 4, right? And then we go back to this Landau model for comparison, right? So we have seen in the last video that the beta function for this quadratic coupling constant, right? So this rho m was defined as the adimensional mass coupling, right? So to speak, right? The beta function for this guy is given by this expression, right? And this was the gamma for the phi square operator in 4 dimensions, which is given here in lambda phi 4. It's just lambda over 16 pi square, right? And we also know that the running for this coefficient of the phi square part, right, is given by this equation, right? Which then we can use to solve. You just have to plug the beta function here. And remember, this is an approximation. There was on other terms, right? This was the leading contribution below 4 dimensions. Right? Now, if we plug this beta function here, right, we get this equation, right? And that's what we have to solve for, right? So let's start by looking at the simplest point, which is near the Gaussian fixed point. So you go to the perturbative limit, right? And near that point, lambda is very close to 0, right? This is dominated just by the scaling, right? At that point, this term can be ignored. So my differential equation becomes just this, right? I can take this term away. And that has a very simple solution, right? Which is that rho bar m of p, remember I'm putting my momentum with this thing below so we don't forget, is just rho m, which is some constant, times m over p squared, right? This is the solution to this differential equation. This is okay, but it is just a very complicated way of writing something we already know, right? Remember, this guy was defined as to make some adimensional Wilson coefficient out of m squared. So I define this in this way, right? Rho m times the renormalization scale, right? Just to define something adimensional in front of the phi square operator, right? That before had m squared, right? If I substitute these over there, right? Just take rho m is equal to small m squared over big M squared, and I substitute here, I just get a different expression for this guy, which is m squared over p squared, right? And that's exactly what I expected, right? So this is the Wilson coefficient for the phi square interaction, for the phi square interaction, right? And this will become important as the momenta are comparable with the mass, right? If the momenta are much bigger than the mass, then this coupling goes to zero, as we expected for a relevant operator, right? It becomes important at low momenta. That's all I'm saying here, right? But that allows us to define a typical momenta when that happens, right? I can say that I'll define some rho of m of some momenta, which I'll call here p0, right? This is not the zero component of the momentum, it's just some particular momentum, right? Where this function is of order 1. This 1 is not important. I could put any number here, a, right? I'm just saying that this is not 0, right? That's when this quartic part of my potential becomes is important, right? If this is order 1. And that at that scale, right, we can say a few things. I can use this relation to say that m square is p naught square, right? Over p naught square is 1, right? Which means that, as I already said, that p0 square is equal to m square, right? Which can also be written as rho m times this scale m square. And that's why you don't need 1 here. If you had an a, b, any number here, right? It would be just together with this m square, which is already a arbitrary scale, right? The important thing is that if you talk about typical momenta when this term is relevant, right? We know that correlation distances are the inverse of this typical momenta, right? So I can define my correlation distance from this theory, right? If I want to match it with the Landau model, the Landau theory that we had before, I can use this P0 to define my correlation length, right? Which in this case will be of order m to the minus 1, right? Or written in other ways, right? If I solve P0 here, this will be m minus 1 rho m minus half, right? You can be worried at this point of the importance of this one, how big is m, but none of these facts matter. What I really want to look is this, right? Because what I'm saying here is that as this parameter changes, as I change the intensity of this coupling that is in front of the phi square, the correlation length goes with that to the minus half, right? So psi is again scaling as the coefficient of the phi square term to the power of minus half, which is exactly what we had right here, right? So at least very close to the free theory point, right? And you see, I disregarded in both cases, I disregarded completely interactions, right? I set lambda to 0 essentially in the lambda phi 4 side. So I'm really only looking at scaling and symmetries for my theories, right? And I got the same result, that namely that correlation lengths grow, right, as 1 over this guy, this 1 over the square root of this coupling, right? In this case, I could just assume that this guy is temperature dependent, right? I need some kind of dependence for this coefficient, right? But now there's a much more interesting behavior at another fixed point, right? Remember that we also found, right, for dimensions lower than 4, that lambda phi 4 had a fixed point. We called that fixed point lambda star. So now I want to look what happens if I go near the point where my coupling is lambda star. We'll see what happens. The equation I have to solve is the same. So I have to solve for this one, right? But now instead of this thing here, I'll just leave the gamma function, right, of phi square calculated at lambda star. Right? That's the differential equation I have to solve for the running of this guy, right? So now the solution to this equation is very similar to the one we had before, right? But instead of having here, we had this solution to the power 2, right? Now I have a different, and remember, this is just a number, right? Just calculate gamma at that point, at that non-trivial fixed point. So now my rho m bar is, again, a constant times m over the momenta, as before, right? But now I have 2 minus an anomalous dimension, right? Which again is playing this role of changing the scaling of something, right? So again, if I use the same definition, right? Let's look at the typical, at the value, look at the system at the value of momentum where this thing is of size 1, right? Which again is just a way of saying it's relevant, it's not 0, right? I'm not at very high momenta and just when I can just forget this quartic part, right? If I do this and calculate what's the size of this P0, right? Now I have to solve for this, right? That means that rho m over P0 to the power 2 minus gamma of phi star should be 1. And now I want to solve for P0. But before, I want to rename this nu to the minus 1, right? Just calling 2 minus gamma nu to the minus 1, right? And then I can solve this. Right? It's just easy, just raise everything to the power of nu, right? And then I get P0 is equal to rho m to the power nu, right? Times m. And now I can do the same thing I did here, right? My correlation length now is of order P0 to the minus 1, right? Which means that my correlation length now scales at m to the minus 1 times rho m to the minus nu. Again, this is not important. If I had a number here, it would be dividing, right, this mass, right? But the important part is how psi changes as I change the Wilson coefficient. Because now I'm not getting the square root, right? So this nu to the minus 1 was defined as 2 minus the gamma function calculated at this fixed point, right? Now let's use what we know, right? So this guy is lambda over 16 pi square. So this is 2 minus lambda star over 16 pi square, right? And this lambda star, we calculated the fixed point for this theory, right? Lambda star is 16 pi square over 3, 4 minus d, right? Below 4 dimensions. That's the position of this fixed point. Let's substitute that here. That means I get 2 minus 1/3 of 4 times 4 minus d. And of course there are other terms, right? We have disregarded higher powers of 4 minus d, right? Everywhere, consistently, I hope. Now let's compare this with what we had before, right? Well, our conclusion here is that when we are at the Gaussian fixed point, C scales as this coupling to the minus half, which in terms of the Landau theory means that psi scales as T minus Tc to the minus half, right? But now near this other point, this fixed point, right? We are getting a different behavior. This is scaling as rho m to the minus nu, right? Which should translate to a solid condensed matter system as psi scaling as T minus Tc to the minus nu. And nu is, right? This is the definition of nu. Nu is just equal to 1 over, right, over 2 minus 1/3 of 4, 1/3 times 4 minus d plus other contributions of order 4 minus d square, right? And of course you can see that as I go to 4 dimensions, right, exactly 4 dimensions, this goes back to the minus half that we want, right? But you have corrections that go beyond the Landau model, right? In fact, this point is known as the Wilson-Fisher fixed point, because Wilson-Fisher have shown how to even go beyond this leading order in 4 minus d and systematically calculate higher order corrections, right? We could include, in fact, we could have calculated these for more complicated theories, right? So we assumed our material here had just one direction of magnetization, right? Which gives it just a very simple symmetry, right? But if you went to theories with more directions, right, and which were symmetric in these various directions, you could impose a ON theory, right, for n directions, right? And then the same calculation would lead to a nu minus 1, which was 2 minus n plus 2 over n plus 8, 4 minus d plus higher orders, right? And you can see that for n equal 1, which is the symmetry just in one dimension, right? We go back to this 3 over 9, which we have right here, right? But you could use this to describe, right, for n equal 1, we're talking about just one direction, right? But you could take some material that which has a preferable magnetization in a plane, or just an isotropic material in which all the 3 directions are completely equivalent, and use the same approach, right? In fact, if you do that, right, you would get for d equal 3 now. Let's just put d equal 3 and calculate the size of nu, right? You could build a table, 1, 2, 3, right? And now I just put I just put this in this expression, right? And calculate what nu should be at this approximation, right? So in the Landau theory, it's just 1/2, so 0.5, right? But if you calculate it using this one, right? This will be 0.6, 0.63, and 0.65, right? And this is all really independent of the material. You're only really the only information of the material is how symmetric the magnetization is at long distances, right? As you look away from the details. So Peskin and Schroeder's book includes a very nice and long table on this, right? It's on chapter 13, if you want to look, right? But let me just quote a few examples, right? So for n equal 1 system, which includes some binary liquids and some type of brass, right? The experimental value for nu is 0.625 for this binary liquid and 0.65 for the brass, right? So you see very different materials and this exponent, which is what we call, by the way, I'm forgetting to name the guy, right? This is the critical exponent, right? Which I have advertised at the title of the video, right? This is how the correlation lengths in the material change as you approach the critical temperature. So that's a critical exponent, and it is not 1/2, right? You can see experimentally this is closer to the quantum field theory calculation than to the Landau model. In fact, that's the quantum field theory approximation at leading order, right? If you do a proper, more involved calculation, you include extra corrections, then the theoretical numbers change. So in this case, the theoretical number would be 0.63, right? In this one, the theoretical one would be 0.67, and in this one, the theoretical would be 0.705 at a better approximation than what we did here, right? So you see the agreement. For n equal 2 systems, you have some complicated materials here. So for n equal 2, some superfluid helium, right? The experimental value for this critical exponent is 0.672, right? Uncertainty is here. See how close it is. And for n equal 3, there are some materials here. It's very, very complicated materials. I don't know what to call them, but you see there are measurements like 0.7 or 0.72, which are really close to this one. So this idea that very different condensed matter systems could have the same exponents seems magical, right? Seems like a huge coincidence until you understand the renormalization group equations, right? Because what's happening here is that the effective, when you go away from the microscopic details of the material, right? The irrelevant operators go to 0. All you get is the relevant operator, which is this phi square right here. And the phi square sets this exponent, right? The symmetry of the system sets the exponent, not the details about the UV. Right? And then you understand how very different materials could have the same critical exponent. That's the universality, right? And this translates to the same question that people were having in high energy physics, right? Why our theories, I mean, the theories that work at low energies, I mean, far away from the UV, from the cutoff, are just these renormalizable theories. It's the same, right? It's the same answer, because what is happening is that only at long distances, only the symmetries of the problem really matter, and they are setting the shape of these renormalizable operators, right? Which ones are present or not, right? Here, this is just one of many critical exponents I could define, right? If you're really curious about a complete treatment of that, you can take from the quantum field theory point of view, you can take a look at chapter 13 of Peskin and Schroeder, right? Where they define a bunch of other critical exponents, and which is the scaling of different quantities instead of just the correlation length, right? But that's beyond the scope of our course, right? And that's it for today. Thank you.